I'd like to introduce our speaker. This is Dr. Paul Lehner. He's a senior principal scientist at the MITRE Corporation, as well as one of our leaders on the adoption and ethics thrust at AI-SDM. Dr. Lehner is an expert in the field of artificial intelligence and its application to societal decision-making, and has over 3 decades of experience in conducting research and developing innovative solutions in this area. Today, his talk, which is, I love this title, When is Using AI the Rational Choice? He'll be speaking to us about his latest research on the use of AI to support societal decision-making, and he'll be sharing his insights on some of the challenges and opportunities of using AI to improve decision-making processes. So at this point, I'll turn it over to Paul, and Paul, take it away.
All right, thanks, Norm. Just one last sound check. Sound okay?
Yeah, everybody good?
All right, moving on then. So yeah, I'm Paul Lehner. I work for the MITRE Corporation. We are one of the participants in the AI-SDM. Just for your all information, MITRE Corporation is a $2.2 billion nonprofit corporation, but you didn't know we were that big. We operate federally funded research and development centers. And when we do work outside of that umbrella, we basically need permission from what we call our sponsors. We don't have customers, we have sponsors. So we operate multiple FFRDCs, one for DOD, Health and Human Services, DOJ, NIST, FAA, IRS, and a few others I can't remember. And if you're interested in what an FFRDC is, just Google NSF FFRDC list, and it will give you the entire list of all the FFRDCs. We're kind of contract. And you may be surprised to know that the national labs like Los Alamos, they're all FFRDCs. Okay, just to give an idea of what we do, we tend to be a trusted financial conflict-free advisor to our government sponsors. And so I just put this up as a random example. What you see on the right is a government HHS site that has something called CDS Connect. CDS is Clinical Decision Support. They maintain a repository of what they call knowledge artifacts. These are essentially elements of a knowledge base for a clinical decision support system. And actually, as you can see in the write-up, they specifically mention MITRE and our Health FFRDC as the organization that maintains it for them. That is the usual position of MITRE. We help them do what they want to do. Okay, as for myself, my PhD is in mathematical psychology. I laughed when you said 3 decades. I'm older than that. And my dissertation work actually was in the game of Go, AI playing in Go. That was kind of fun. I do have a smattering of publications, somewhere around 40 in journal publications, but I'm not an academic, so I tend to publish when I have a reason to make a point. And so you'll see that if you ever look me up. My other current work right now, which I'm really proud of, is we're preparing a set of instructional modules for intelligence analysts. And there's at least one agency that's going to push it out to all their analysts worldwide. And essentially, we're teaching critical thinking skills that are Bayesian derived. And you can think of it as, from Bayes theory, you can pretty much derive the critical thinking skills that comprise of the scientific method. Well, here we're doing it for analysts, okay? I've had a few senior positions. I was a chief engineer for the IRS FFRDC. Yes, I was part of bringing you a kindler and gentler IRS, and that is a running joke. I worked in the government for a while at a place called IARPA, etc. But I'm old, and there are a few technical topics that I want to get resolved before I retire. This happens to be one of them. All right, that's enough. So we're going to talk about the adoption and AI decision support, the MITRE work. Everything I'm going to show you is stuff we done under the auspices of the AI-SDM Research Institute. But first, I need to give you some background. Before the current machine learning wave, there was a literature on expert judgment, mechanical judgment, and how to use it for advisory decision support. Let me give you a quick summary of that literature. Statement 1. Simple statistical models routinely outperform expert judgment in forecasting and other judgment tasks. And if you're not sure what a judgment task is, just intuitively, anything you would call a judgment call, that this really applies. Just to give you a couple of quotes, Hastie's and Dawes' textbook, Rational Choice in an Uncertain World. Notice the reference before the current machine learning wave. Enormous and almost unequivocal research literature implies expert judgments are rarely impressively accurate and virtually never better than a mechanical judgment rule. And they said typically a simple linear model. Actually, I'm not sure if that was me, but I know what they meant. Second, this is a meta-analysis by Grove, and for the life of me, I can't remember the reference right now. But you can see basically the similar kind of results. Occasionally, experts do better than simple mechanical models, but it's not common. And it doesn't depend on the type of task, the type of judgments, the amount of experience, or anything else that you think might be an important variable. So that's been known for quite a while. In fact, you could go back to 1954, and Paul Meehl had a book that, I just looked this up on Google, it'll pop up immediately. It was a meta-analysis of studies to that point that showed a lot of these similar kinds of results. So this is as old as the dirt. We know this to be true. The other thing we know to be true is that these models are rarely used by experts. As it's saying Hastie's and Dawes' book, almost all of these findings have had almost no effect on the actual practice of expert judgment. So the machine learning community, and I've seen papers to this effect, has rediscovered that models can outperform experts. They build some good models, they do better than the experts that they're competing against, so to speak. You're not the first to discover it. I'm pretty sure you won't be the last. But this research is motivated by trying to avoid the second part, a lack of practical impact. At which point you might say, what the heck am I talking about? You can't turn around without bumping into an article or some kind of press release that talks about all this great practical impact of the current machine learning applications. How could I possibly be talking about a lack of impact? Well, some of us are old enough to remember the 1980s, wave of AI expert systems. Expert systems are essentially knowledge engineered systems. Actually, CDS Connect is an example of that. Essentially knowledge engineered systems that were designed to replicate human expert decision-making for the purpose of being an advisory system. So like a medical diagnosis advisor. There was a huge amount of publicity and funding around AI expert systems, easily matching today's huge amount of publicity and funding for machine learning applications. Lots and lots and lots of reports of applications. Everybody knew this was going to change the world until it didn't. And I think it's the latter half of the 90s, it all kind of came crashing down, and we entered the period called the AI winter. In the 80s, if your proposal didn't say AI, you weren't going to get funded. In the 90s, if your proposal accidentally mentioned AI, it was the kiss of death, you were not going to get funded. So the important message here is, while a lot of this stuff is great, great work, I have no doubt about that. In fact, my dissertation was in Go. I love AlphaGo. But don't take the current press as actually strong evidence of many successful applications. It may be, it may not be. But the press itself is not a good indicator. What we anticipate is that some types of machine learning applications will crash and burn. And I'm talking about a category that I call trustworthy. And simply put, the people who should benefit from the application would benefit, society as a whole would benefit. It should be used, but won't. Our research is focuses on predicting when and where it won't be used when it should, and how to avoid that. All right, so let's, one more thing here. So the question is, why is it sometimes difficult, or often difficult, to get AI to be used in an organization? Often the explanation is some version of organizational change is hard. In fact, I just listened to what I thought was a very nice AI maturity model that MITRE has put together. And it points to a lot of these things. It's ineffective change communication, you have a change resistant culture. There's a long list of these kinds of things. And I think they're all true. I don't have any objection to any of that. But I'd like to point out, this has been going on since 1954. That's an awful long time and across multiple generations to explain the lack of use as being irrational, as resistance. We have a different explanation. And bear in mind here, we're talking about advisory systems, so things that actually help a decision maker. Experts often avoid using advisory systems because it is the smart thing for them to do. It's the rational choice. Our research hypothesis is that an expected utility analysis that considers all relevant factors, I'll define that shortly, will largely predict whether an AI machine learned capability will be used and how that usage will evolve. And we're going to go through enough here to show you how we're going to do that. But first, let's talk about all relevant factors. Okay, so somewhere in the middle, let's take the example of a clinician in medical diagnosis. Just put words to it. Here's your clinician. They have to make a decision. Are they going to use this advisory capability or not? Well, what impacts their decision? Well, certainly benefit to their patients is an important variable. They consider the patient's values when they have to make that decision, but they operate within an organization. That organization, say a hospital, has to worry about things like malpractice implications. I mean, there are a variety of things they have to worry about. Beyond that, they operate within a societal context. We worry about things like equity and fairness across different societal groups, other issues related to ethical decision-making. So we have societal factors that impinge on organizational factors, plus the patient factors that all kind of, narrow down to this one person or one class of individuals who have to make a determination. Is it worth using this capability? Now, these are dotted lines because sometimes the consumers are the ones who use the device, so they would make the decision. Sometimes an organization like a hospital will just say, there is no way you can use that. If you've ever been in when you're thinking about, for example, Medicare, I did some work with them a few years ago. There are certain classes of AI applications they will avoid like the plague because of these societal issues. Okay, so that decision is taken out of the hands of the clinician. But you get the idea. Lots of factors impact the decision. Should I use this thing or not? Now, how do we analyze that decision? I'm going to introduce here a notion called a use pattern. I'm going to give examples from radiology, but let me just assure you that this is not limited to radiology. It's just easy to show in this way. And well, just let me push through it. And in a few slides, just to give you a heads up, I will actually give you a live demo of an analysis. Okay. So an example of a use pattern. The machine reads the images from a case. The radiologist simply accepts it. This is a use pattern that's often quickly rejected, and I think we'll explain why that's the case shortly. The machine reads the imagery. It explains its recommendations and outputs to the user. The radiologist looks at what the machine says and makes her assessment. This is an often mentioned approach. This is from Liebig. The machine does its reading. If the machine is confident, the radiologist says, yep, I'll go with that. If not, the radiologist makes the judgment herself. I actually got data in this one. Another one. If the machine makes its assessment and then it provides a digital display that overlays pointers and circles and all that kind of good stuff on the image to grab the attention of the radiologist, and then the radiologist decides. That's another pattern. Another pattern. The machine and radiologist do their thing independently, and then after their job is done, there's some kind of algorithmic merge of the two. That's another pattern. The variation of that, they do their thing independently. If they disagree, then there is a final assessment that's based on relative confidence in the AI and the decision maker. And there are a variety of variables that go into that confidence calculation. But you can see this is good stuff. It's a PNAS publication. I mean, it's all cool. And notice that word complementarity here. That's going to turn out to be really, really important in the next few slides. Now, I should point out, this is 1, 2, 3. All 6 of these have a common ethical problem, which I'll describe shortly. But the 7th use pattern is specifically designed to get around the ethical issues associated with the first 6 use patterns. And this approach is they each do their thing independently, and if they disagree, bring in another radiologist. Okay, so I think you can get the idea of use patterns here. Oh, by the way, use pattern is not common terminology. It's unique to us at the moment. But you can get the idea of different use patterns all using the same basic underlying AI capability. Now, we're going to talk through this use pattern, the accept if confident use pattern. This illustrates how we're going to do this. Once again, I'm going to promise a live demo shortly. So, another concept I'm going to introduce, counterfactual misses. But first, let's look at this. The accept if use pattern based on the Liebig paper. Actually, I'm going to do a quick sound check. We still good, Norm?
Yep, you're good. We can hear you.
Okay. Every once in a while, I get worried I'm talking to nobody. So, okay. In that particular paper, I smoothed over sensitivity specificity. I just back of the envelope this. But basically, the AI was about 87% accurate. The radiologists tend to be about a little more accurate, 90%. When the AI expressed self-confidence, it was about 97% accurate. The net result is if this use pattern, the acceptive confident use pattern is used, the combination of machine and radiologist is about 92% accurate. That's cool. That's a 20%, because of 10% of the times they miss it. So now they only miss it 8%. That's a 20% reduction in missed cancers that are now correctly diagnosed. There's a corresponding improvement in false positives. And it's easier, faster, less workload. What could possibly be wrong with this picture? And the answer is counterfactual misses. Without going through this, I'll tell you exactly what this is. Patient has cancer. The machine confidently said no cancer. The radiologist accepted the confident no cancer judgment. But when the cancer later manifests and it becomes obvious, and they go back and look at the images, the radiologist looks at it and says, how could I have missed that? I would have seen that if I had looked at it myself. When she gets pulled in for a peer case review, her colleagues are going to look at that and go, how could you have missed that? It's clearly there. That's a circumstance where she's going to be reprimanded, because remember that medical ethics issue I mentioned? Clinicians are supposed to make the final judgments themselves. They are not really supposed, according to medical ethics, to defer to the machine. In effect, what she did in this circumstance is defer to the machine. And as a result, you got this counterfactual miss. Now, on balance, deferring to the machine in this way gets you a net positive. But for those few cases, I estimate this will happen about 2 or 3 times a week. For those few cases where you have this kind of counterfactual miss that you wouldn't have gotten it wrong if you'd looked at it yourself, all kinds of bad stuff happens. And I could easily see a radiologist saying, look, I know this thing works, but I just don't need this kind of problem. I'm just not going to use this thing. I don't like getting sued. You get the idea. Now, how do we analyze this kind of accept if use pattern? I mean, how do we know this is going to materialize in my, sort of informal characterization? So now I'm going to start getting into the modeling approach. So let me just build this quick. So at the caricature level, here you get the AI, the strength of output, distribution of the strength of output is higher when the patient actually has cancer versus when they don't. The radiologist has a similar profile. Here, the radiologist is a little bit less accurate. Their threshold set, and if you go past a certain threshold, then the AI is confident, and the radiologist says, yep, cancer. Below this other threshold, negative, radiologist says, yep, no cancer. Anywhere in between, she decides. All the counterfactuals and all these issues about counterfactual misses are related to the sensitivity and specificity of the radiologist in those cases where she deferred to the AI. Okay, so all the interesting stuff is happening outside the bounds. Now, I'm going to show you I ginned this tool, put this tool together for purposes of this presentation, but it pretty much shows you the pieces that we're kind of thing we're talking about here. We're going to start here, a couple of static slides, and then I'll get to a live demo. We're going to start here with an assumed characterization of the decision maker and AI capability. Here, I just put in, D prime. If you're a psychologist, D prime is the normalized difference between the means. Different disciplines have different labels for that, but this is just a normalized difference between the means, and you can just specify it. For reference, you can quickly calculate the corresponding AUROC. We set thresholds, those two thresholds I mentioned. Base rates are important, although not hugely important. And then there's productivity boost, because if the machine says got cancer and the radiologist says, okay, that's my diagnosis, a lot less work to do. There's a productivity boost under that circumstance. On the utility side, well, here's it from the patient/consumer's perspective. Have cancer, diagnosis, have cancer, great, you may have saved my life. Have cancer, diagnosis, don't have cancer, that sucks. Okay, you may have killed me, that's a -10. This is where all those societal organizational factors get crunched into at the moment. We'll spread this out later, but this is specifically the counterfactual missed positive cases. Have cancer. The combination of person, a radiologist, and machine using this use pattern said, yep, no cancer. But turns out, if she had looked at it later, she would have discovered, she would have known, I'm sorry, if she had looked at it at the time without using the machine, she would not have made this mistake. So that's the really bad circumstance. We're giving this a -50 here. That's a.
What is EF?
Is there a question?
Yeah, what is F key?
Oh, I'm sorry. So in quotes, it's what's said. The first one, the F, is the what is the diagnosis from the machine plus user. So because the machine said high confidence, no cancer, that was the actual diagnosis that was made. The second one is what the radiologist would have done if she had done it on her own. So cancer, the diagnosis is no cancer, but if she had done it on her own, she would have said, yeah, I see the cancer. She would not have made that mistake. Does that help?
Yep, thanks.
Okay, that's just, sorry, I'm not making this coding clear. I'm so used to this kind of coding. I sometimes make this mistake, sorry. Now, there is some relative importance to the radiologist for the patient's values and her career. And so that's kind of, how you weight these two. This looks harsh, like the patient is only 10% the value of my career, but really, this is really a measure of how much you're willing to risk your career for the expected benefits to the patient. I've shown this to others and they thought that was generous, so I'm sticking with 0.1. Okay, now you got that. Now the last thing that's important here is complementarity. Complementarity 0 means redundant. Since they're equally accurate, that means the AI and the person get the same answer on all the cases. They always get the same answer. It's completely redundant. If you have an AI capability that is completely redundant with the expert, you will never get that 20% boost, the 20% fewer missed cancer diagnoses, because they always agree. You only get a benefit to using the AI on a case-by-case basis is if they disagree. Sometimes the AI is correct and the radiologist is wrong, and sometimes the AI is wrong and the radiologist is correct. They disagree. What this use pattern in effect does, as to all the use patterns really, is it separates out those two. It helps you figure out which one to listen to when they disagree. And that's not exactly how in sequence they do it, but that's the net effect. It provides some discrimination. When they disagree, which one do you pay attention to? Any use pattern that's going to push you toward paying attention to the one that tends to be more correct when they disagree will get you a net benefit with increasing complementarity. So the complementarity scale goes from completely redundant to completely independent. I don't need to define that here. I'm sure many in this room know exactly what a conditionally independent is, and this is just a mixture distribution. Anyhow, moving on. Okay, so those are the inputs. And now let's talk about the outputs. For this particular set of settings, the 0 point here is what the unaided decision maker, in this case, the radiologist, would do without having any AI helping her whatsoever. Since the AI is exactly as accurate as the radiologist, there's a no net benefit, no net loss. Okay, same benefit from the consumer's perspective. This is the consumer patient's perspective. From the consumer/patient's perspective, when you use the AI according to this use pattern, this accept the AI if it's confident, otherwise do it yourself, what you see is as complementarity increases, this is the 0 to 1 scale here, the benefit to the patient increases. Okay. And that makes sense because the use pattern has the net effect of listening to the AI when it's very likely to be correct, and listening to the radiologist when the radiologist is likely to be correct. It makes that discrimination. So cool. And this is exactly what you saw in some of those other papers. They point out the importance of the AI and the radiologist disagreeing and picking the right one when they disagree. Now, this is going back from the decision maker, the clinician's, the radiologist's perspective. Should she just accept the AI's advice and do nothing else? And the answer is no. You can see it's bad. And it again goes off the chart bad with barely any levels of complementarity. And that's because this counterfactual miscircumstance happens way too often. So never do that. But this is from the perspective of the clinician, the radiologist, of using it according to this use pattern. Well, it's negative, and it gets worse with increasing complementarity. Why? Because, well, if you have disagreements, you not only have opportunity for getting the right one, but you also have opportunities for these counterfactual misses. They may not happen very often, but they're so bad that they drive the expected utility per case negative. So the radiologist would, in this circumstance, would be crazy to use this device. Furthermore, everything I just mentioned so far is on a per case basis. But when you fold in productivity, it gets worse. It's the old joke. I'm losing money on each sale, but I'll make it up on volume. Well, here, the net effect is negative for each case. So why would you want to run more cases? So basically what you see here is, given these parameter settings and this basic use pattern, the best situation for the consumer, for the patient, is actually the worst situation from the perspective of the radiologist. You shouldn't want to use it. All right, now let's play with some numbers. I'm going to try to run this live here for you. Give me a second. Okay. So here's the spreadsheet where I have these calculations. First, oops, wrong one. First, oh shoot, come on, move this over. I can make this work, trust me. Move it over some more. All right, sorry. Okay. There we go. Okay, the first thing is, if you make the thresholds conservative, you can improve the situation from the decision maker's perspective, but it provides less value to the consumer. So let me just do a couple of these. So I'm making the lower threshold lower and the higher threshold higher. And the net effect, you can see it here. The value to the consumer it's positive, but not really a lot. But at least from the decision maker's perspective, the radiologist's perspective, it's a net positive. So, you should use it. It's a net positive, even from her perspective. It's not strong, but at least it's positive. Okay, second observation. Let's put these two back. Okay. Second observation. Asymmetric thresholds, as it turns out, actually fixes this problem. And that kind of makes sense. If the problem is counterfactual misses, well, just never believe the machine when it says no cancer. Just totally ignore it, no matter how confident it is. That's what this setting does. And the net effect of that setting is still great for the consumer, and still positive, not hugely positive, but on the right side of zero for the clinician, for the radiologist, for the decision maker. Under this circumstance, they should use it. And this is also an example of how we can predict evolution of usage over time. If this use pattern is adopted in the way I initially described, this would predict that over time, The radiologist will simply learn to ignore the AI when it says no cancer and only listen to it when it says cancer, because that's the smart thing to do. That's the rational choice. So that's an example of how we would predict evolution of usage over time. But wait, there's more. This thing is robust, and this is important because you can. I mean, I used to be a decision analyst, so I know how to ferret out these utilities. But really, you don't want anything dependent on exact utilities. This use pattern is robust. Let me make this minus 1,000. Well, it didn't budge the important ones here. Why? Because we've already totally avoided this cell, these counterfactual misses. So no matter how badly you can get sued, it won't happen because you've avoided the suits to begin with. All right, let me put this one back. But the coolest observation here, I love this part, is the accuracy of the AI is not the big driver here. I'm going to take this and push it down as far as I can, 1.5 standard deviations, because anything lower gets literally throws it off the chart. And as you can see, this is the one I really care about. From the consumer's perspective, even though the AI is considerably less accurate than the radiologist, it is still of benefit to the consumer, to the patient, for the radiologist to use this capability. Okay, it's about 70–75% of the benefit we got when the AI was just as accurate as the radiologist. And it's still a net positive from the radiologist's perspective. Once again, not hugely net positive, but being on the right side of zero is really important. And so what this is telling you is that if you use an AI capability, an advisory capability, even if it's not that great, if you use it in the right way, it is something that should be used and we would expect will be used, because the utility from the radiologist, from the decision maker's perspective, is positive. Okay, back to the main presentation. That was your live demo. That was it. Okay, now let's clean up a few topics. Cognitive biases. So experts are overconfident. They routinely believe themselves to be more accurate than they are. I mean, we all do this. It's not just experts. I'm fond of saying it's pretty easy to build a forecasting model that's more accurate than an expert. It's really hard to build a forecasting model that's more accurate than experts believe themselves to be. Okay. But what's important here, you noticed, so I'm sorry, let me slow down a second. So you would expect that an expert, the radiologist, believes herself to be more accurate than she really is. She would probably believe herself to be more accurate than the AI, even if that's not true. However, given what I just showed you, where the accuracy of the AI was way less, yet it was still worth using, that tells you that that use pattern, even if she has an incorrect assessment of their relative capability, she should still use it. That is robust. That use pattern is robust against this cognitive bias. Similarly, let's see, time. Okay, this is just for fun. If you're a psychologist, this is old news. If you're not, it's probably new to you. Memory biases. We tend to believe we predicted things we didn't. Typical way to test this: you go to an election, before an election, take a month before, and this is not a political statement, but say, all right, who do you think is going to win the House in 2024? Republicans or Democrats? And let's just say you answer me, yeah, Republicans. How certain are you? 55%. Great. Wait for the election to happen. Let's say Republicans win the House. Wait 2 months. Go back to that same person, say, remember that prediction I asked you to make? Yeah. What did you say? I said Republicans. How certain were you? Oh, I was pretty certain. I said like 70%. That 15% miss swing in a false memory, they're not being disingenuous. That is what they remember. Memory tends to drift, and that's not an exaggeration of the effect. Memory tends to drift in the direction of what actually happened. Now imagine when you bring this down to counterfactual misses, where the question is not, what did you say, but what would you have said? I'm pretty sure people are going to tend to say, yeah, I would not have made that mistake, even if they would have. Therefore, they're going to think there's a much higher proportion of counterfactual misses than there would really be. And that would really kill the system if you didn't have it set up so that counterfactual misses didn't cause a problem. And that's what we did in that last demo. We set this, the asymmetry to the thresholds such that counterfactual misses, even if you think they happen, would happen a lot, you've avoided them to the point that this no longer becomes a problem. So that use pattern is actually robust against these cognitive biases. And you can do that for lots of them, and you get the basic idea. Cognitive biases don't tend to work in the favor of using AI unless you have a use pattern that is robust against those biases. All right, moving on, almost done here. I just wanted to give a quick example in a different domain, just so you don't think we're only talking about medical diagnosis. So MITRE, we have a center called Center for Advanced Aviation System Development. That's the FAA, FFRDC. And basically nothing's changed in the air traffic control system in the US that hasn't gone through MITRE in, say, the last 30 plus years. Okay, they did some machine learning work to predict runway excursions. Plane lands, it lands poorly, it runs off the runway and into the ditch or into the river. That's an excursion. That's not great. They did some pretty good work. So on approach, 30 seconds out, maybe a minute out, but on approach, they can give an alert that says, you're given the current conditions and whatever you're doing, you are at risk of a near excursion event or an excursion event. So they did a pretty good job of predicting those. Nevertheless, despite the fact that the machine learned model was decently accurate, pretty good AUROCs, it wasn't used. And the reason it wasn't used is when you pulled in the utility considerations. You're in a domain where excursions are rare. There is a cost to pulling up and diverting from a landing. People really don't like that. And no matter how they played around with it, the net utility was negative. It was a perfectly good capability that was not used. I can't say that if they'd done a modeling of the kind of like I just showed you, they would have avoided this, but they might have. We could have at least have anticipated that. And I am going to go back to these folks. I was on their advisory committee a few years ago, and see if we can redo the analysis and see if we can come up with a different answer. But just want to let you know that this kind of analysis is not at all limited to the medical context that I was using to explain it. Okay. A couple of notes on empirical testing. I don't have time to go through this, but basically, this is intended to be a predictive model based on what the right rational choice is. There's sort of two levels of predictions. There are macro predictions. So take medical diagnosis. That's a broad area, but everything I just mentioned, those are probably issues that are going to be common across the area. Therefore, we would predict pretty much across that kind of application domain, certain problems are going to reoccur, certain kinds of things are just not going to use. That will be a macro prediction across the domain. And we're collecting data on different domains, trying to get a sense of some of those, I would call them gaps in AI usage. Eleanor, at MITRE is actually running the data collection, so I just want to give her a shout out. Then there are micro predictions, which we're nowhere close to yet, but this is a particular device, a particular AI application intended for a particular user in a particular context. So we could analyze the specifics. In fact, the FAA one I just gave, the runway excursion one I just gave, would be an example of a specific application, and we could do a similar analysis there and see whether the predictions we make hold up. Will it be used or not? Let's see. We're reviewing some different literatures. This is on the macro level. I think the judicial decision supports is kind of interesting because there are models for predicting sentencing, for doing sentencing guidelines, for predicting recidivism that are used for parole decisions. Those are hotly debated as being societally biased, and you may have different definitions of bias, but it's hard to imagine that these things aren't a big concern from a societal bias perspective. Nevertheless, they're widely used. In fact, they're mandated in like 6 or 7 states. They have to be used. And what we're saying is simply that if there are poor decisions that come out of this model, despite all of these societal factors, the decision maker here, basically judges and parolee boards, are largely immune from the negative consequences of those societal factors. So they use them, and that's how I'm interpreting it so far. That's a quick reach because I'm no expert here, but just moving on. Okay, moving on. Ramifications. This is fun. So what does it mean to say AI is trustworthy? Because you hear this word all the time, at least around MITRE you do. Well, trustworthy AI is a feature of the AI itself. Should it be used or shouldn't it be used? Trusted AI is a feature of the person who's going to make a decision whether or not to use it. Knowing when to trust the AI is basically the perspective we have, that a rational choice analysis basically says you get your benefit when you have a way of interacting with the device, so you know when to listen to it and you know when to ignore it. And that's the circumstance in which you get the most bang benefit for the buck. If your focus is on knowing when to trust, then maybe you might consider a little different perspective on the learning or objective function you use when you typically do some machine learning. I mean, often you see attempts to optimize on the ROC curve, but if knowing how much you should trust the output is the key variable, then perhaps calibration should get a lot more weight than it typically does. You know, calibration, when it says 70%, it happens 70% of the time. Well, that's something a user can make sense of. So just something to keep in mind, that when you have a use pattern, expected rational choice analysis perspective, it actually might change what you want to put in as your learning function when you're doing your machine learning. Ethical AI, this is kind of fun. So there's a distinction to be made between primary ethics, benefit to patients, and secondary ethics, basically the means to get the benefit to patients. In the medical arena, the notion that clinicians must make their own final diagnoses, well, that's clearly intended as an ethical principle that leads to better value on the primary ethic. But what I just showed you before is that ethical principle was getting in the way of getting benefit of the AI capabilities to the patients. So when we introduced AI capabilities into that mix, there became a disconnect with a current secondary ethic and the primary ethic. And it would recommend a change in that ethical principle. And I do believe a rational choice analysis of the kind I showed you can help you guide your reasoning through how you should change your ethical principles in this kind of circumstance. Okay, and then of course we're MITRE, so we're going to eventually release a tool that lets you do everything I just showed you, because we're systems engineer, that's what we do. Okay, future connections in the AI. I mean, I'll eventually get to talking all use cases because I don't understand your utilities yet, so that'll be fun. I just wanted to mention that I was particularly intrigued by Terry's presentation on the simulation setup they had over at Howard, because they do include some of these societal factors, and I think there's an opportunity to test our predictive modeling, the rational choice-based predictive modeling in that environment, TBD. Okay, and that's basically it. Oh, good, I made it. Questions?